or should I start the recording because you'll have
I
to?
did.
Okay, awesome. So, hi everyone. So we have about 11 people now, so I guess we'll get going. So we have a very special guest speaker today. This is Dr. Alexandra Abanov from Stony Brook University, professor of physics. If you'd like to introduce yourself further, please feel free to.
Sure, I'm working in condensed matter physics. So the idea of condensed matter is to try to understand qualitative and quantitative new features which appear when you put a lot of molecules and atoms together. And this is partially related to the subject which I'm going to talk about today. And I work in Stony Brook University. I used to be the competitor in various type of physics competitions. And we now still have some club where we also prepare people to and teach them how to solve high school physics problems. So this I have in common with you guys. So let me start. Let me start by sharing my screen and okay, share sound. Okay, and okay. So this is the title page, and presentation mode is here. And I hope you see my cursor so that I can point things out. So my topic today is the emergence of geometry and topology in physics. Uh, well, I'll explain what all these words mean just in case not everybody knows the same in the same version as I do. And the question which we're going to address in this talk is that so we have the concept of emergence in physics, mainly when macroscopic properties are very different from the properties of the particles constituents of the system. And we also have understanding what geometry and topology is and some idea of quantum physics. And the question is, what will happen if we bring all these things together and try to see whether geometry and topology themselves can emerge from quantum physics or classical physics, doesn't matter. So let me first introduce the main players of the game. By the way, I hope this will be as informal as possible. Please feel free to interrupt me at any point, ask questions. I will have some breaks for questions, but please ask me at any point. There are a few of us and we can afford that. So emergence. So let me start with a quote from Richard Feynman, one of the visionaries in physics. The quote is that nothing is really as it seems, and he was basically saying that the one of the things that make it science difficult is that it takes a lot of imagination. It is very hard to imagine all the crazy things that things really are like. Nothing is really as it seems. We are used to getting hot and cold, and all that is the speeds that the atoms are jiggling. If they jiggle more, it corresponds to the hotter, and colder is jiggling less. So this is a typical example of emergence that I will keep in mind. Uh, so um, the general idea of emergence in philosophy and system theory, emergence occurs when the whole is greater than the sum of the parts, meaning that the whole has properties its parts do not have. And in physics, it's more specific. We usually say that emergence is the way to describe a property, law, or phenomenon which occurs at macroscopic scales in space or time, but not at microscopic scales, despite the fact that macroscopic system can be viewed as a very large ensemble of microscopic systems. Okay, so just pictorial description of what emergence is that if you look at this picture, let's start from the right of the screen. So you see some pixels here, black and white or some grayish, and you cannot tell what it is, but if you zoom out and out and out, then you will see that this is actually waterfall, in fact, in Ithaca. So essentially, looking at the system at large scales, we see some features which we do not understand looking at small scales. And that's what I want you to think about when we talk about emergence. And another property, more physical, is that the temperature is the property of a macroscopic system. It does not make sense to talk about temperature but the feeling of hot and cold appears as a result of averaging over fast motion or jiggling in Feynman's words of molecules. So if the average kinetic energy is high, we feel it as hot. If it's small, we feel it as cold. So any questions so far? Is it too elementary, too slow? Comments? Okay, let's move on. Geometry and topology. Well, I'm pretty sure that you all know what geometry is and topology, but I want to really describe it a little bit and introduce a couple of concepts from geometry which I will need for my particular purposes. Well, we'll start with the definition that geometry is from ancient Greek, which is measuring the earth, but it is a branch of mathematics which is concerned with questions of shape, size, relative positions of figures, and the properties of space, according to Wikipedia. And earlier, geometers were basically working with properties of lines, points, and figures in space. In modern geometry, we usually study spaces themselves. So the space is endowed by geometric properties such as distance, proximity, and people study various relationships between those properties and prove various results concerning those relationships. So our focus here will be the emergence of geometry itself. So when we have something which does not have geometry, but then geometry appears as a result of physics. So that's the idea. And we will start with simple examples of modern geometry concepts, which are, say, parallel transport, connection, and curvature. Okay. Do many of you know what parallel transport, connection is, etc.? In any case, I'm going to talk about it in more or less detail, at least give you some idea what it is. So we're going to talk about what's called intrinsic geometry. So let's assume that there is an ant which is crawling on the surface of a sphere, and the question is, can ant, without going into third dimension, find out that his space is curved? Okay, that there is a curvature of that sphere, that it's not flat. And we are going to do that using the idea of parallel transport. Okay, so what we are going to do is we are going to ask, can we transport vector parallel to itself from point A to point B? And on a plane, there is no problem. We just connect it with a straight line and move vector in such a way that the angle is between vector and straight line is preserved. So what are we going to do on the surface on the curved surface, like on the surface of a sphere? We actually do essentially the same. We will connect the points A and B by the shortest possible line, which is called geodesic line. And in the case of spheres, these are the great circles, the circles such that they appear as the intersection of a plane going through the center of the sphere with the sphere. And this AB is the shortest possible path from A to B. And then we basically will transport the vector parallel to itself along the shortest curve between two given points, such that we will preserve the angle between the vector and that curve at all times. Okay, and then we will get a vector from point A to point B, and we will call it parallel transport. Okay, so already here you can see quite an interesting thing that let's try to transport vector from point 1 to point 3 through the point 2 and then back in a closed loop. Let's start with this vector, which is shown here at point 1, and transport it to point 2. Well, the shortest path is this piece of a meridian, and we will transport the vector and we will get this vector. Then we will transport this vector to point 2, preserving the angle 90 degrees in this case with equator. And then we will transport this vector to point 1 again, and we will get this vector. And you can see that the vector we get is not the same as we started from. If you transport the vector parallel to itself on the plane, you will definitely get back to the same vector. But here, the vector rotated counterclockwise, if you look from top, by 90 degrees of pi over 2. And we will say that if vector is rotated, we will say that there is a curvature. So the space is curved. That's a signature of curvature. In this particular case, we can even quantify. We say that the rotation of the vector is pi over 2. The area surrounded by the path is the eighth of a full spherical area, which is 4 pi r squared divided by 8. And if you divide this angle by the area, you will get 1 over r squared, and we will say that curvature is 1 over r squared. Of course, I use the fact here that the curvature is the same at all points. Therefore, I just took the big path and divided. If I wanted to measure curvature locally, I would just take a small circle here, or small path, closed loop, measured the angle of rotation of the vector, and then divided by the area, and I would get curvature at that particular point. Okay. Just simple remark of arithmetical nature, but it will be useful later, and it's quite deep. If you take the curvature, which is 1 over r squared, according to our definition, and multiply it by the full area of the sphere, by 4 pi r squared, you will get 2 pi times 2. Okay. Let's remember that. We'll come back to that next one. Okay. Now, what do we do in general? Suppose I have a general surface and I want to transport vector from A to B along this particular path. Well, this path is not the shortest path between A and B. So what I'm going to do is that at every point of the path, I will draw the local geodesic line tangent to the path, the shortest possible way, but tangent to this particular point. And locally, I will translate this vector along this small, tiny piece of geodesic, preserving the angle with geodesic. Then, after I do that, I will have another piece of the curve. I will do another geodesic and transport vector parallel to that one and to that one. And sooner or later, I will get vector from point A to point B. And I will call it vector transported from A to point B. Okay? Does it make sense? Any questions? So we do not know how to compare two vectors. If you have two vectors at the same point, you can compare them. You can say that one vector is rotated relative to another. You can compare their lengths. If length of vector is defined, you can just see whether these vectors are equal or not. You cannot compare vector at point A and point B. They're just so different, so you really don't know how to compare them. This vector is tangent to surface at this point, and this vector tangent to surface at that point. But what you can do is you can transport this vector parallel to itself along some particular path and find out what you get at that point from that vector. That's parallel transport, what parallel transport is about. Or we say that we have a connection, the way to transport vectors along curves. So for any curve given on a surface, I know how to transport vector parallel to itself from one end of the curve to the other. Well, using this connection, I can do a very interesting trick. I can take a vector, transport it around closed loop, and then I get back to the same point. And at the same point, I can compare two vectors, and I can in particular measure how much the vector is rotated. Okay. So using connection, I can actually do the trick which Ant did, transporting the vector parallel to itself along the closed loop. And let me introduce one more concept, which is curvature or Gaussian curvature, which is the following. You just take the small loop and transport vector parallel to itself around this small loop and divide the angle by which vector rotated by the area of that loop. And we call it curvature at that particular point. So what we can actually do, some exercise we can do, we can take this arbitrary shaped surface, take curvature at this point, multiply it by the area of this cell, and then sum over all cells or integrate. Okay, so I will call it this way. This integral, this is the curvature at the point, and this is the piece of the infinitesimal piece of the area surrounding this point. And I want to cover the sphere with this unit, with the cells, and sum up all this, take this integral of the curvature of the surface of the sphere. And remarkably, the answer will be 2 pi times 2. Although this surface is not a sphere at all. The curvature is very different here. It's bigger, it is smaller, but integrated curvature still gives you 4 pi. Okay? And that's a very deep mathematical theorem. And this is a remarkable result. The integral is the same no matter how you deform that original sphere. Okay? Do you know this fact? This is called Gauss-Bonnet theorem. And it's one of the most remarkable results in math. Okay, so why is it 4 pi, and what should I do to change this 4 pi? Can I take another surface so that it's not 4 pi? And it turns out that the answer to this question is related to the idea of topology. So let me say a few words about topology. So again, in mathematics, the topology is a part of mathematics which concerned with properties of space that are preserved under continuous deformations. So basically, you have to assume that the world is made out of rubber, and you can deform things any way you want, but you're not allowed to cut or glue things together. But any deformations are allowed. If there is some property which does not change under such deformations, it's called topological invariant. Okay. Can you come up with any topological invariant? So any example of some things which
Would volume be one?
volume? Definitely not, right? Because you just take the piece of material and
Oh wait, yeah.
volume
Holes?
is, say it again.
Holes?
I don't know here.
Holes.
Holes. Yeah, sure. Yeah, and that will be my example. Actually, that's probably the simplest one example. You can talk also about dimension. For example, if you have some three-dimensional stuff and you stretch it, it will still be three-dimensional. So dimension is one of those. The number of pieces is another one. If you take some piece of material and you are not allowed to glue or stretch, then the number of pieces is invariant. So there are quite few invariants of the topological nature, and topology studies properties which do not depend on the deformations. But the distance, area, volumes themselves are definitely geometric, but not topological properties. Okay. So, for example, the curvature of the surface is definitely geometric property, right? Because if I have a sphere and it's curved, then I can flatten it, and it will not be curved. So I can put some dent in it, and it will be curved in the opposite direction. So the curvature is geometric property. It's not topological. But what previous example shows is that the integral of the curvature of the whole surface is much more robust. For example, the integral over the surface which is obtained by deformation of the sphere is still 4 pi. And this property is called Euler characteristics, and it is a topological property. So what we learned now is that we can start with the property which is called connection, the way to parallel transport vectors. We can make out of this property curvature, which is the rate of rotation of this vector when you go around small closed loop with respect to the area of that loop. It's called curvature. And curvature is geometric property, but if you integrate curvature of the whole surface, you will get some topological invariant, which is called Euler characteristics. So this is how this Gauss-Bonnet theorem looks like. It tells you that if you have a closed surface, there is a generalization for open surfaces, but let's do closed surface only, and integrate curvature over closed surface. Then you get 2 pi times some topological invariant, which is called Euler characteristics of the surface. And this Euler characteristics is just 2 minus 2g, where g is the number of handles or number of holes. So if you have a sphere, the number of holes is 0. You get here 2, and 2 times 2 pi is 4 pi. If you get the torus, so bagel, then g equals 1, chi equals 0, and you get 0 if you integrate. And indeed, you can basically, you can see at torus that curvature is positive here, but negative here. But the result is that on average, if you integrate it, you will get 0 identically. And if you have g equals 2 holes, then you will have minus 2 here, and the integral will be minus 4 pi, which means that on this surface, the curvature is mostly negative. Okay? And so on and so forth. So this is an example of the connection between geometric properties. When they integrate that out, they give you some global properties which are topological. Any questions?
So if it's negative versus positive, what would the difference be?
Yeah, so that's a good question. I did not talk about it, but basically, if you have a surface, then locally you can think about 2 circles which approximated the best. And like if you have a piece of sphere or something like this, you have 2 circles, and the center of those circles lie on the same side of the surface. Okay, then we call it positive. And in this case, if you take vector and go around, it will rotate counterclockwise. If you go counterclockwise, the vector will rotate counterclockwise. That's positive curvature. Well, you can imagine some surface
Oh,
such that if you take a vector and go around counterclockwise, the vector will rotate clockwise. And in the curvature is general concept for any dimensions, but in 2 dimensions it's especially easy. It just means that one curve has a radius on one side and another curve on the other side, which is usually can be visualized as saddle. Like if you think about horse saddle, this is precisely like this. It has one curved surface with the center at one side of the saddle and another one with the center on the other side. This is a typical example of negative curvature. Yes. Okay. Other questions? Okay, let's move on. So now let's go to our first example of emergent geometry, and we will talk about falling cats. So I used to have the whole lecture about how cats land on their feet, and let me give small piece of that lecture. It's a really rich topic. So it's called cat writing reflex. Again, in Wikipedia you can find it, and it's a cat's natural ability to turn itself around as it falls, so that it will land on its feet. Well, cats actually start doing this at 3-4 weeks of age, and by half a year they do it perfectly well, and it's quite amazing. And the paradox it seems like a paradox, because you can take the cat and drop it upside down with 0 angular momentum in the beginning. So the angular momentum is supposed to remain 0 because of the conservation of angular momentum, and there is no external torque acting on the cat. But cat nevertheless manages to reorient itself and land on feet. So it might seem paradoxical a little bit. It definitely does not work the same way with the conservation of momentum. If you want to change the position of the center of mass of the system, you need external forces. You cannot do it. If initial momentum is 0, you will not be able to change it, and you will not be able to move center of mass of the system. But the overall angle you can change. And that's quite deep phenomenon, interesting. And first of all, let's just see how cats actually do that. And this is a very short video from BBC. Please take a look. Okay.
This caracal is about to do something that would seem impossible. All cats have a remarkable design, a flexible spine, which allows them to rotate their front and back ends in different directions at the same time. As it falls back to Earth, the caracal creates a clockwise rotation in the front half of its body, but the back spins in the opposite direction. By spinning in 2 different directions at the same time, the caracal is effectively pushing against itself. But it does even more. Like a spinning ice skater, it pulls its front legs close, which makes the front half of its body spin faster. This creates a twist in its spine, allowing it to swing the back legs round and prepare for landing.
Houston, the Eagle has landed.
Okay. So the last piece is actually quite amazing. It's different part of physics, how to land softer, but it's very nice movie. So as you can see, the cat actually changes its shape quite significantly. And actually you can prove very simply the theorem that if the absolutely rigid cat released upside down without initial push will never be able to land on its feet because of the conservation of angular momentum. But it turns out that if you allow the shape changes, then you can make the total angular momentum of the cat composed from the angular momentum of its different parts, which are independent, and then you can manage to reorient. If you look at the Wikipedia article about cat writing reflex, you will see even some simple illustrations there of how it works from the angular momentum conservation point of view. But for us, it's important, but it's pretty kind of obvious what cat does. This is the algorithm. So basically, cat bends in the middle and rotates front half in the opposite direction than the rear half. So the angular momentum is conserved. But tucking the front legs to reduce the moment of inertia of the front half and spreading the rear legs at the same time to increase the moment of inertia of the rear part, cat is able to rotate the front part by bigger angles than backwards rotating the rear part. And then cat does opposite. Cat spreads the front legs and tuck in the rear legs and continue doing the same thing. And at the end, it can basically very effectively change the total orientation in space. Okay, what does it have to do with geometry? Yeah, let's first just look at this. This moment exactly illustrating this. You can see how this cat spreads the rear legs to increase the moment of inertia and tucks in the front ones. Okay. Any questions? Then we'll try to connect it to geometry and connection and parallel transport, etc. Okay, this was actually quite controversial subject, how cats land on their feet. There was some theories that the cats rotate their tail, and of course it in principle are possible with the tail as was shown, but it turns out that cats without tail do it as well. So it's cannot be the only explanation. Then pushing against air, of course, was considered also not correct, etc., etc. But that's changing shape is the right answer. Okay, let's move on. What does it have to do with geometry and previous topic? So first of all, let me say that it's very difficult. If I give you cat of two different shapes and I ask you what angle it rotated by, it's a hard question. However, it's very difficult. It's very easy to answer this question if the shape is the same. So if cat has this shape, then let me attach some two axes. I mean, I'm showing this two-dimensional illustration. You can attach three axes and have full three-dimensional story. So let's attach two fixed axes to this particular shape. Then if cat has the same shape, then I can just look how this axis rotated, and I just can say that the angle of rotation here is something like 45 degrees clockwise. Okay, this cat compared to that one. So if shape is the same, it's easy. What if I have two different shapes? How can I say that one shape is rotated angle 30 degrees compared to the other shape if shapes are totally different? This question does not make much sense at all. But what we can do is we can take all possible shapes of cats and attach two or actually three axes to each shape, like infinitely many shapes of cats. Let's take in an arbitrary way, attach three axes to each of the shapes. Okay. Then, so for any particular shape, we know what these axes are, and then we just compare different shapes by comparing those axes. Like for example, I'm asking what is the angle of rotation of this cat compared to this one. Well, I just say, okay, I look at the axes attached to those shapes in advance, and these are the two axes attached to that one, and these are two axes attached to cat B. So rotation is something like, I know, 15 degrees counterclockwise in this case. Okay. Of course, this is very arbitrary. I mean, how did I attach my axis here? In arbitrary way. So there is some part of arbitrariness here, but nevertheless, I can, for any shape now, I can tell what's the angle of rotation of this shape compared to the initial one. Okay. So, yeah, this is how we do it. So we know we have some canonic way to attach axes, and we just can compare this to cats by comparing those axes in state instead. Okay. So now let's suppose that I give you the path. I will tell you precisely how cat changes shape to go from A to B. Then knowing this precisely, in principle, it's not easy technically, but in principle, I can use Newton's laws and conservation of angular momentum to find how, what will be the orientation of the cat when it is in shape B in space. And having my axis attached, I can just say exactly by what angle or angles this cat rotated compared to that one during the particular specific motion and changing shape, the particular change of shapes. Okay. So which means that, of course, this results strongly depend on how I've chosen my axis in the beginning. But we know how to deal with this. We just say that, okay, but for closed paths, when cat goes back to its original shape, I can actually objectively find the angle of rotation. So what I'm saying is that we actually, in the first part, we, using Newton's law, we define connection in the space of shapes. And the second part, when I go in the closed loop and look at the objective angle of rotation, I have some kind of curvature of that connection. Okay, this is hard concept, but think about this. Think about the space of all possible shapes of cat, of a given cat. This is infinitely dimensional space. It's not one, not two, not three-dimensional. There are not one, not two, not three parameters which define shape, but many. So it's like infinitely dimensional space. In that space, the path in this space means the particular sequence of shapes of the cat. Knowing the path in this space, I can solve Newton's laws, Newton's equations, and find actually what the orientation of the cat is. And having pre-assigned triplets of vectors to each shape, I can now formalize it as some angle of rotation of the cat in space. So for any path in a space of shapes, I have the angle of rotation, which means that I have connection defined in the space of shapes. And looking at the closed path, I can define curvature of that connection. Yeah, so I have some geometry here because connection and geometry are connection and curvature are geometric concepts, right? So, and what actually defines that geometry? Newton's laws. Because to really find the connection in the space of shapes, I had to use Newton's laws here. Okay, and that's my first example of very simple. Well, the geometry here is not very simple, but the simple example of geometry appearing as a result of physical laws. So if I think of this as a representation of the space of shapes, this is the closed path in the space of shapes. I can introduce some kind of area of this and look at how the angle of rotation of the cat changes with that area. The concept of area is not pretty clear there, but at least what I can do is I can take a closed loop and tell exactly what will be the angle of rotation of the cat in space. Okay. Any questions so far? Okay, so let me just summarize. There is a space of all possible shapes of cat. This is my geometric space that I want to study. I attach arbitrary orientation to each shape. Newton's laws give me the motion of a cat if the path from shape A to shape B is known. We can compare the final orientation of a cat in shape B with the canonical one, and that defines the connection in the space of shapes, some angle corresponding to each path. The result strongly depends on the arbitrary choice of axis in the initial step. But for the closed path, the change of orientation is very well defined. We have a curvature of the connection, and the curvature does not depend on our arbitrary choice in the first place. And Newton's laws result in geometric structures, connection, and curvature in the space of shapes of a cat. Okay, so geometry in this case emerges as a result of physics of Newton's law. Okay, so any questions? Okay, let me move on to some quantum example, which is my favorite part of physics, quantum Hall effect. And this is how electronic transport and geometry emerge in the result of quantum physics. So let me first give you some very quick introduction. So quantum Hall effect was discovered in 1980 by Klaus von Klitzing, who got Nobel Prize for this in 1985. Notice that just 5 years passed from the discovery to the Nobel Prize. This is very rare these days, and this shows that people immediately recognize the importance of that discovery. And then moreover, another Nobel Prize was basically resulted from the discovery of fractional quantum Hall effect, which is some modification, very non-trivial modification of the integer quantum Hall effect originally discovered in 18. Okay, so the whole thing has something to do with exotic quantum fluid. So electrons on the surface of semiconductor form some very exotic state, which is called quantum Hall fluid these days. And let me first explain you what classical Hall effect is, although you probably studied that in school. And that is a very simple thing. It was discovered by a student, Edwin Hall. His advisor recommended him to do these measurements, and he did it. And that's why it's called Hall effect. So the idea is the following. Suppose that you have a piece of material, and you basically send current through this material. And you can measure voltage drop along the material. And you divide voltage by current, and that's called resistance, right? So what Hall asked or was asked is that what happens if you have magnetic field perpendicular to that surface? Then you know when electron moves, there is a transversal force, which is Lorentz force, acting perpendicular to the velocity and magnetic field. So the electrons will feel the force in this direction. And the result, there will be some voltage drop in the direction perpendicular to the current. Okay. So what you can do is you can measure this voltage drop and divide it by current. And this is called Hall resistance. So it has the same dimension of ohms, but it's a voltage drop across the current in the presence of magnetic field. Now, suppose that I change magnetic field. It's not surprising that because this force is proportional to magnetic field, then the Hall resistance, which is called Rxy. Xy means that current in X direction, voltage is in Y direction. So this Rxy is linearly proportional to magnetic field. And that's what Hall measured. On the other hand, if you measure longitudinal resistance Rxx, so both current X and voltage drop is in the same direction X, then you will get more or less constant. It depends a little bit on magnetic field because electron paths are curved, but it's more or less constant. And this is Ohm's law. Okay, so this is what Hall discovered. This is what typically people expect in this setting, in the electronic measurement in the magnetic field perpendicular to the sample. Okay, and our question is the following: what will happen to this Hall effect in extreme conditions? And extreme conditions are really extreme. First of all, we will consider almost two-dimensional sample when electrons are really only on the surface of semiconductor. And in quantum physics, it's possible to do it exactly in some way. I will not talk about it. Suppose that we have very clean samples, almost no impurities. This is very hard, but people achieved quite remarkable results in cleaning semiconductors for industry. So these are these samples were the cleanest samples available at that time for that experiment, and very low temperatures, like 1 Kelvin or so, and very strong magnetic field, about 10 Tesla, 1 Tesla to 10 Tesla. Okay, suppose that I have these all conditions very extreme, and we will do measurements. So what we will get, and this is what we get. This is experimental plot, and it seems to be a mess, but there is a very beautiful plot. Let's compare it with the classical picture which we expected. Okay, so Rxx is a blue line, horizontal, almost doesn't change, and instead of that you will get this line, the low line. This is instead of blue one, and instead of red one, which is supposed to be more or less linear, you have more or less linear growth of Rxy with respect to magnetic field, but at some point there are plateaus, like really horizontal pieces of the curve. Okay. Moreover, they measured what resistance it flattens at. So what is the value at this plateau of Rxy? And it turns out that it's about 25 kilo ohm, but not just 25 kilo ohm, it's 25,812 point, etc., with 1 out of billion accuracy. And you do different samples, you repeat this experiment, you measure resistance at this plateau, and it deviates only in part 1 in a billion. It's extreme precision. And you have to understand that although I said very clean samples, there are a lot of impurities, there is some dirt, but somehow this particular quantity is absolutely insensitive to that dirt and produces the result with amazing accuracy. In fact, this quantity now is used as a standard of electricity, as a standard of electrical resistance. So instead of using as a standard some piece of material which is, I don't know, in some safe somewhere at fixed temperature, people say now, if you want a standard of resistance, make a quantum Hall setup and measure this piece, and this will be your 25 kilo ohm. This is what is used as a standard now. Moreover, this particular quantity is equal to the Planck constant, which is the main constant in quantum physics, divided by electric charge of electron squared. This has also dimensions of ohms, and it's precisely equal to this quantity. So the question is, how does this semiconductor and electrons know about this h divided by e squared, about fundamental constants only, and absolutely not sensitive to the impurities, etc. Okay, before we go to that, let me just say that in addition to this one, there is also another plateau at 1/2 of that quantity, at 1/3 of this quantity, at 1/4 of this quantity, and this is called integer Hall effect. But if you can make your sample even cleaner, as in this case, then you see that there are also plateaus at various fractional parts, which are called fractional quantum Hall. And the explanations of integer and fractional are quite different. It's somewhat, and fractional involves some fractional charges of electrons. Okay, that's an amazing story on its own, for more than one lecture probably. But so let me move on to my particular purpose. Any questions about that so far? Have you ever heard of quantum Hall effect? I really think this is one of the most fascinating discoveries of the second half of 20th century, say. Okay. So, so this is quantum Hall effect, and the question we want to ask is that, is any reason, how can we explain that the system so imperfect, there is some particular crystal with impurities, surface, semiconductor, and it gives you h over e squared with such an accuracy? Is any particular reason why this accuracy is so high? And the answer is that that it is related to some emergent geometry and topology of in this transport, adiabatic transport in quantum Hall. And what we're going to do is we're going to repeat the so-called Laughlin's argument, slightly modified version. And this Laughlin argument is what gave him Nobel Prize of 1998 for fractional quantum Hall. So it's like a setup which no experimentalist, no sane experimentalist will do, but we can imagine this, and this is better for theory purposes. Let's assume that I have a surface of a bagel, and my electrons live on the surface of a bagel, on the surface of a torus. Okay. So this will be my quantum Hall sample, surface of a torus. And what I'm going to do is, it's hard to apply electric field. It's hard to connect this battery to this torus without destroying the torus itself. So instead, what I'm going to do is I'm going to take a solenoid, like piece of wire in the form of solenoid, and I put it through one hole of the torus. And I put another piece of wire, a piece of solenoid in this, inside the other hole of the torus. Okay, so inside this torus. Remember that electrons on the surface, and the magnetic field which is required by quantum Hall effect is perpendicular to the surface at every point. Okay, that's my setup. Now, think what will happen if I change current in this solenoid, which I called X solenoid. So you change current, the magnetic field inside this solenoid will change in time. The flux of magnetic field through this hole of torus will change in time. You know that when flux changes in time, the electric field around it will appear, right? According to whatever equation, so Faraday's law. So electric field will be along the torus, along the bagel. when you have electric field like here, in the presence of magnetic field, electrons will move perpendicular to that electric field around this part of the torus. And they move in the presence of the flux inside this, so we'll go around a magnetic field inside this solenoid, and that will allow us to measure something. In any case, what I can do with this device is I can take my fluxes, which are essentially currents in solenoids, and change this phi x and phi y as two independent parameters by changing currents in solenoid x and solenoid y in time. Okay, I'll do it very slowly, and I will take some point which is characterized by some particular values of those fluxes, and I will slowly change currents in those solenoids so that the system will be characterized by the flux which moves around the closed circle, and I come back to original point. Okay, do you understand the setup? Any questions about that? Okay, then quantum mechanics comes in, and in quantum mechanics you describe the system, no matter how complicated it is, by wave function, okay, which is some complex number. So I'm not going to go into quantum mechanics, no time, but if you know what complex numbers are, and I presume you do, then the main idea you will understand. So it is a complex number. Complex number, you can think of this as a vector, which has a length, which is called absolute value of complex number or magnitude. And it also has the angle, like it's like a polar coordinates, the angle, which is called the phase of a complex number. Okay. So what you can do is you can take those fluxes, perform the closed loop in the flux space, and ask what will be the wave function of this many billion of electron problem when you come back to the original point. Well, roughly speaking, the wave function will come back to itself, because I move everything so slowly that nothing almost changes. It's all adiabatic. That's why we call it adiabatic transport. Adiabatic means that you change something very slowly. So I come back to original point and I look at the wave function. But what I can see is that this wave function can change its phase. So it can be sort of rotated. And it turns out that this angle of rotation is proportional to that area in the flux space of the contour. So what you can see is that for any loop, I can measure the change of the phase of the wave function. That's my connection. For closed loop, I see that the change of that phase is proportional to the area, and the rate of that is called curvature. So I have my old friend curvature appearing as a result of complicated many-body quantum physics. The curvature appears in flux phase space. Okay? That is really, I mean, this is what Nobel Prize was given for. So this is maybe hard to understand. So ask questions if it helps. So the wave function changes along the closed path in the space of fluxes. This connection. Curvature has a meaning of Hall conductance. This is what Hall conductance is, whatever inverse to Hall resistance. This I do not explain. This is a part of the physics. It's relatively simple one, but I will not explain it no time. But this curvature, which we defined as just geometric, more or less, quantity here, actually has physical meaning that it actually measures the conductance. Okay. And then what we can do is we can do our old trick. We can take this curvature, which we measured at this particular piece, and integrate it over the whole flux space of all this square. If you really think about it, then it turns out that there is another major principle in electricity and magnetism, that the flux 0 and flux 2 pi should be absolutely indistinguishable. Okay, let me say a few words here. This is really important. Strictly speaking, you should have asked me how electrons here can at all know anything about the flux through this solenoid, because magnetic field is always inside this solenoid and electrons do not feel magnetic field at all. Well, they still should feel the change of magnetic field, which is the Faraday's law. So that's okay. But in principle, the flux itself should be absolutely irrelevant. Any point here should be the same. It turns out this is not quite the same, that quantum particles do feel flux inside, but only if it is fractional of some what's called flux quantum, phi 0. And if you have integer number of flux quanta of the through this hole, then even quantum electrons cannot feel it. So in fact, this side of this square should be identified with this side of the square, and this side of the square should be identified with this side of the square, and then the flux space is actually torus itself. So this is my real space torus where my Hall effect is, and this is the parameter space which is also torus. And at every point of that torus, I have a curvature, which I computed, as I explained, by looking at the wave function space. Okay. So now what we can do, if we have a surface and curvature at every point of the surface, we can integrate curvature over that surface. And we know that we should get something like Gauss-Bonnet topological invariant. In this case, it's called Chen class. And this Chen class, by mathematical theorem, is always an integer because of that periodicity of flux quanta. So it's always integer. And what I just explained is that if you take Hall conductance and average it over the space of these parameters, then I will always have integer number. And this explains why the actual measured Hall conductance is so close to integer number in some particular units. So the reason for exact quantization of Hall conductance or resistance on that experimental plot is actual topology and some topological invariant underlying this exactness. Okay, so this is just to summarize. So I have some physical system which depends on parameters, fluxes. Physics define connection in the space of parameters for slow change of parameters. This connection defines transport on one hand because it's related to Hall conductance, and the curvature from the geometrical point of view. And the integrated curvature is, on one hand, is topological invariant. On the other hand, it's some physical quantity related to transport, which is Hall conductance. Okay, and for you just to compare how close these examples are from this point of view, is let me do falling cats versus quantum Hall table. So in falling cats, we had a space which was made space of shapes. In this case, it's space of fluxes. Physics in falling cats was rotational dynamics, and that was defined connection. And in quantum Hall, it was quantum interacting electrons in magnetic field in general. And the transport, in the case of cats, cat was changing its shapes, and transport was the rotation of the cat in the ambient space, in the surrounding space. And in quantum Hall effect, the transport is actual transport of electric charge along the torus. And integrated curvature in quantum Hall effect is actually related to some integer Chern number, and this is called conductance, and this is the reason for exact quantization of Hall conductance in Hall effect. It's more subtle than that, definitely. I skipped a lot of interesting points, but this is roughly the Alaflin's argument. Okay. Integrated curvature in falling cats is actually also an interesting story, but that's for some other time. Okay, and any questions about that? Okay, so let me now, the last part, which is relatively short part, I'm almost done, is let us try to speculate on the nature of geometry of our space itself. And let me talk a little bit of some not very established, some of the theories, which is called quantum foam theory, or how the space-time itself, our space-time, our space and our time, emerges from quantum physics. And what I'm going, so basically this is what I'm going to do. We have three major theories of last century, which is special relativity theory by Einstein, the quantum physics, and the gravitational theory, which is also by Einstein, well, which was by Newton. And what happened in the last century is that Einstein tried to combine relativity and gravity, and he got general relativity. And people also combine quantum physics with relativity, and they get what's called quantum field theory. And one example of quantum field theory is standard model, which is the basis of our explanation of elementary particles and physics. And people still work on the combining all of that together and to get what is called what would be called quantum gravity. But there is no final success. There are a lot of progress in recent couple of decades, but still we are very far. So definitely it's beyond the scope of this to give any reasonable introduction to any of this. So instead we will do dimensional analysis. When you solve problems in your club, you probably know that the easiest way to check things is to check dimensions of the left-hand side and right-hand side of the equations and see whether units are the same. And that helps a lot. And it turns out that you can also do some kind of discoveries using this. And so what we're going to do is we're going to try to look at the major fundamental constants related to this physics. In gravity, this is Newton's constant in Newton's law of gravity, classical law of gravity. In quantum physics, this is h bar, which we already, Planck constant, which we already encountered in Hall effect. And in relativity, this is speed of light. Okay. So what we are going to do is we are going to try to see what we can do on the grounds of dimensional analysis from these three quantities. It turns out we can do quite a lot. So these are values of this constant: speed of light, meters per second, g in this funny units, meter cube, kilogram -1, second -2, and h has this value and is joules times seconds. Or basically, if you want to be more abstract, this length divided by time, which is the speed. Gravity is length cube mass -1 time -2, and h bar is this. And what you can do using this is you can combine these quantities in such a way as to get something of dimension of length. You can see easily how to do it. You just multiply this by this, mass will cancel, there will be still time, and then you just multiply by c some particular power, cancel time, and then whatever, you get square root and you get length. And you can just take this and substitute numbers and you get some length, which is quite amazing. Out of nothing, out of some fundamental laws of physics, we get some length, which is 10 to the minus 35 meters. Okay. What is the size of the atom? Does anyone remember?
Is it 10 to the minus 11 meters for a hydrogen atom?
Okay, yeah, 10 to the minus 10, yeah, right, more or less like that. It's in angstrom. Angstrom is 10 to the minus 10, it's more or less like half an angstrom. Okay, 10 to the minus 10 meters, roughly. Okay, this is 10 to the minus 35 meters. So this is so small that even the CERN accelerator does not probe this small sizes. This is smaller than anything by many, many orders of magnitude. So we really cannot have any experiments on this scale at this time. But we can speculate a little bit still. Similarly, with time, you get 10 to the minus 44 seconds, which is just amazingly small. Well, mass turns out to be 10 to the minus 8 kilograms, so it's not particularly small. This is one of the puzzles of modern theories, is why this mass is so big in some sense. Well, strictly speaking, it's a question why gravity is so much weaker than electrical forces. But anyway, we're not going to talk about that. Just from nothing, we get these particular scales. And what we can ask is, what happens at this microscopic scale of suppose that I have microscope which goes to 10 to the minus 35 meters. What will I see? Well, you can argue that because it's made out of these things, that at this scale, the quantum physics, h bar, gravity, g, and speed of light, which means relativistic physics, should be somehow unified and play the same role at this scale. Like at our big sizes of meters, quantum physics does not play a role. At our small velocities, relativity c does not play a role, right? At small masses, g does not play a role. But at these particular scales of times and masses and spaces, all of these guys should play equal role. So they will be combined. Okay, so what is intuition behind this? Relativity is usually saying that space and time actually are not separate, but they form space-time as a unique, like united thing, right? So there is no really even sense to talk about space and time separately when you have large speeds and relativities in place. Gravity tells me that space-time is curved. This is Einstein's gravity theorem. That space-time is not flat, but depending on the presence of masses, it is curved, presence of the energy, generally. And quantum means that everything fluctuates and interferes. So you can probably imagine that at those small scales, there is no idea of what is of this flat space and time which we use. Does not make any sense. Everything fluctuates and interferes. Interferes means that there is a even state which is not this, which is complicated enough, but superposition, linear combinations of all of this, according to quantum mechanics. So you have something like that at the scale of 10 to the minus 35 meters. But when you go to bigger and bigger scales, it becomes smoother and smoother from when you see from outside. And a very big scale compared to that, we see our space and time. We can measure distance, we can measure time, and it almost do not see any fluctuations. So basically the idea is that if you think of this as a microscopic system, then I'm saying that the space and time themselves emergent. So the way we perceive this space and time, distances and times, is just because we do not look close enough. It's like hot and cold with atoms. You feel hot and cold, which is just averaging the kinetic energy of those atoms, because you do not look close enough and see atoms individually. So individually, it would look something like that, but what we feel is a smooth space and smooth time around us. So this is called quantum form theory, and it's got no experimental confirmations of that, but that's some of the things which you can speculate happen at those Planck unit scales. These units are called Planck units. Max Planck was the one who combined this together. He noticed that if you join, instead of G and C, you also use Planck constants, and you can form actually units of space and time and mass. Okay, so just to conclude, nothing is really as it seems. Geometry and topologies themselves can emerge as conspiracy of huge number of microscopic degrees of freedom. We saw few simple examples and ended up with some speculation on our own space and time. And examples were falling cats, which is classical geometry appearing from classical physics, and quantum Hall effect, where some geometry appeared from as a result of quantum physics. And thank you. Okay. Any questions?
Can we see these emergent properties on like an even bigger macroscopic scale? So are there any sort of properties that we can say with physics that we might not observe on our everyday scale, but maybe we'll observe on galactic scales?
That's a good question. I didn't think much about that. I'm pretty sure that the answer is yes, but like, I mean, take any galaxy which consists of a lot of stars. So from some really big scale, you can think of the stars as elementary particles and the galaxy itself as some big object. And this big object in some cases, and I know that for sure, people simulate as a fluid, some very specific fluid of particles which have gravitational interaction between them instead of usual electrostatic collisions. And you can try to even simulate the motion of this galaxy as a fluid. You can have few sources like huge, big, massive stars or black holes of the big size, and you try to think of how this fluid moves around. So these fluid properties are, in this case, are of course those emergent properties which appear on the scale which is much bigger than interstar distances. So it's almost everywhere. So there are always qualitatively new features coming from the consideration of very huge amounts of small pieces. Some of them are more interesting than the others, some of them less. So, but emergence is everywhere. So it's not. What I was talking more specific about the emergence of geometry of various kinds. But the emergence itself is the basis of every macroscopic system. And as people even extend it in the philosophy realm easily, and so on and so forth. Like philosophy and other sciences. There's actually a very interesting paper by Phil Anderson, who is a Nobel Prize winner, one of the main visionary in condensed matter physics, which was a cult paper at some point. It's called More is Different. More is Different, where he argues that basically that every step from one branch of science to the science is organized hierarchically. Like we have a physics, which describes things on the smallest scale, but then there is a chemistry, which really uses its own laws, like laws of chemical reactions, which of course are based eventually on physics, quantum mechanics laws, but people often do not even derive those chemical laws from physics laws because it's too complicated. They just say that new laws apply at that scale. And then you go to biology and so on up to society, etc. And at every point, the leap is huge. So we believe that even in the laws of society, energy conservation still holds because it's coming from physics and it's preserved. But derivation of those laws from the previous hierarchy seems to be impossible in many cases. Yeah. Okay. Any more questions? I see the comments on dark energy and stuff. That's a separate subject. People are still looking for the candidates for dark energy, and well, candidates for dark matter, and trying to explain dark energy fully, either by corrections to existent laws or by some new physics. But well, that's an open question. Okay. Okay. Is there no more questions? Thanks a lot.
Thank you very much. And yeah, we'll upload this to YouTube. We'll blur out the videos, put a link there instead. But yeah, thank you so much.
Okay. Thank you. Good luck with your club and win in the competitions.
We hope so.